All right, my name is Aki, and I'm a programmer at Activision Central Tech. I work with a small team in Portland, Maine, and we tackle performance problems in Call of Duty titles. So today, we're going to be discussing controller-to-display latency. That's the shortest duration in the game client between a player pressing a button and the player seeing the result of that press on screen. Ultimately, the goal is to describe a dynamic throttling system that we added to recent Call of Duty games to reduce controller-to-display latency. But first, we're going to discuss how we measure latency, and then we'll dive into specific aspects of the engine that had to be factored into the throttle. Finally, I'm going to discuss the implementation of the throttle and its impact on a recent game. OK, so if you split the controller-to-display latency duration into steps, first, the player presses a button, and the button gets sampled by the controller at a certain frequency, and the console samples the controller at a certain frequency. And then, at some point during the game loop, the game queries the OS for its controller state. Then the game uses this knowledge of the button press for gameplay logic and rendering, and the final rendered image then gets scanned out to the display, and the display lights up pixels for the user to see. So we're going to call this entire duration ground truth latency. And there's a bunch of ways of measuring ground truth latency. One technique is to use a high-speed video camera. So for that, you instrument the controller with a device that lights up LEDs when a button gets pressed. And then you take high-speed video of the LEDs next to the display showing the game. And then you take the video and count the number of frames between an LED lighting up and the action appearing on screen. Unfortunately, this process is cumbersome because it relies on human frame counting. And also, individual frame latency measurements can vary quite a bit, so you have to take a bunch of samples to get a good average. And it becomes impractical in practice to frame count every single one of those samples. And that's why it's preferable to use a closed loop system. For that, you would use a device that detects both button presses and detects color changes on screen with a photodiode. So you modify the game engine to toggle the color of an on-screen square based on button presses. For example, switching between black and white when you press the A button. The device then times the button press and times the color change on screen and subtracts the two to get total latency. This process can be more precise than frame counting if the photodiode is sampled at a higher frequency than the video camera. And it's also easier for collecting enough samples for an average to converge. So shown here is the Ben Heck latency monitor for Xbox One. It has a bar of LEDs that can be used with a high-speed video camera. And it also has a photodiode that detects color changes on screen. Also, please check out Benjamin Goyette's talk from GDC 2016 for a deeper dive into latency measurement and how they've been used in past Call of Duty titles. OK, so now we have a way of measuring ground truth latency. Now, let's look at this subset of the latency duration between the game's input query and the final image scan out. I'm going to call this segment in-engine latency, and we can measure it totally in software. So the idea is that the engine timestamps across the frame and then lines up the timestamps based on internal frame index. So here's a latency measurement overlay that I added to Call of Duty Black Ops 4. Each row of the graph represents a single frame, and the graph scrolls up over time. And horizontally, we're measuring milliseconds with the right edge aligned to the video scan out. Each of the colored segments correspond to various engine events that contributed to that particular frame. So for example, the left side of the bright red bar represents the input sample. And so you can see it's sitting at around 20 milliseconds. So that means that in-engine latency is around 20 milliseconds in this example. OK, so now we have a way of measuring both in-engine latency and ground truth latency. What about the segments that we're not measuring in software? Well, the first part is handled by the controller hardware and the console manufacturer. And the last part is handled by the display manufacturer. The behavior of the game engine itself shouldn't have any impact on these segments. In fact, given a stable hardware setup, the total latency contribution should average out to a constant. And we can test this by comparing in-engine measurements and ground truth measurements. So here's a couple of measurements of the game running with different latency parameters. The first column shows an average of a bunch of ground truth samples, while the second column is an average of in-engine values. And if you subtract them, you get about 44 milliseconds of difference. And that means I'm getting around 44 milliseconds of latency contribution from factors outside of the game. And the fact that this difference is constant and independent from the game is really, really useful. It means that we can rely purely on software measurement during development, checking ground truth values only for final confirmation. This significantly speeds up iteration time and makes it easier to log and automate measurements. So moving forward, we're only going to be focusing on how to reduce in-engine latency. Okay, so one more thing before I get into engine specifics. Running at a constant 60 FPS has been a cornerstone of the Call of Duty franchise, and a ton of engineering effort goes into creating as rich of a gaming experience as possible while holding 60. But there's this intuition that performance is a trade-off with input latency, that you can improve performance, but it'll cost you latency, or you can improve latency, but it'll cost you performance. And that's true to a certain extent. That's because one of the most important ways that we fit more content into the game is by making full use of the available hardware. That means directing as many CPU and GPU cycles as possible towards game content. More pixels, more triangles, more physics, and so on. And some of the optimizations we make to improve hardware utilization do introduce latency into the engine. Our goal today, though, is to claw back some of that latency without sacrificing performance gains from these optimizations. So by the end, I hope to show that the trade-off is not between latency and performance. Rather, it's between latency and resilience to variance in performance. Okay, let's get into engine specifics. So to achieve high hardware utilizations, our games are very pipelined, with steps running in parallel on multiple timelines. And here by timelines, I mean the CPU, the GPU, the video scanout. So the best way to think about latency at a high level is to follow the flow of data down that pipeline. So let's say that input gets sampled near the beginning of the top timeline. The result then gets processed and passed down to the next timeline in a chain of producers and consumers until the final image shows up on screen. So the point of pipelining is that you have multiple frames in flight at once, increasing the chance that all CPU and GPU cycles are put to good use. So while we're working on this frame, another frame can start and be in flight as well. So the duration from the input sample to the scanout is the total in-engine latency for this particular frame. And here's the strategy we're going to be employing for latency reduction. We're going to introduce a throttle right before the input sample. By adding a delay here, the input sample gets squeezed closer to the end of the frame, thereby reducing latency. So to make thinking about this throttle a little easier, let's split the latency duration into two categories. First, I'm going to call work. Work is the time spent actively processing something for this specific frame. For example, game logic or rendering. It's the time represented inside the colored boxes. Everything else, I'm going to call slop. Slop is not necessarily idle time. It's usually segments where one timeline is working on a previous frame, or when one timeline is waiting for another timeline to finish work for this frame. So if you look at a generic producer-consumer system, the producer performs some work for this frame, passes it on to the consumer, and then begins producing the next frame. But if the consumer is consistently slower than the producer, the system becomes consumer-bound. The consumer's timeline stays full, trying to keep up with the producer, but the producer is allowed to get as far ahead as possible. And this is why slop exists. The producer is ahead of the consumer, so there's a gap between when the producer ends and when the consumer begins for that frame. How far ahead the producer can get depends on how much buffering is allowed in the system, and exactly when the producer and consumer acquire and release access to the buffered data. On the flip side, slop usually disappears when we're producer-bound. That's because the consumer timeline is freed up. As soon as the producer finishes a frame, the consumer is allowed to start immediately, and there's no slop here. So when you delay the input sample, slop gets squeezed out, starting with the first segment until it disappears, going to the second segment, and so on. Work, on the other hand, gets shifted forward in time, but the total work duration stays pretty much constant. So the key behavior of the throttle is that it squeezes slop while preserving work. All right, so we've split latency into two categories, work and slop. Our strategy is to throttle the input sample to reduce slop, thereby reducing latency. So to figure out how much we're going to have to throttle, we're going to examine all the sources of work and slop in the engine. All right, let's start by looking at what happens at the end of the latency duration. So the game renders a final image into a piece of memory called the frame buffer. The video scan-out hardware then reads the frame buffer top to bottom, row by row, and transmits pixel data across the cable to the display. The scan-out transmits continuously at a rate matching the refresh rate of the display. So conventional displays have a refresh rate of 60 Hz, so the frame buffer is usually scanned out at 60 Hz as well, or once every 16.6 milliseconds. And most of that 16.6 millisecond duration is spent actively transmitting visible pixels. But there are also brief pauses where transmitted data doesn't correspond to visible pixels. First, at the end of every row is a short pause called the horizontal blank, or H blank. And then after the last row, there's a brief pause called the vertical blank, or V blank. These pauses were physically necessary on old CRT monitors, but they still exist today for legacy reasons and for transmitting metadata to the display. So if we put this all on a timeline, you get scan out, then V blank, scan out, then V blank, scan out, then V blank, and so on. And this all happens at a fixed 60 Hz. All right, so now we know that the end of the latency duration is fixed. It occurs every 16.6 milliseconds, and that means we can predict in advance exactly when the scan out will begin for this frame. So our goal now is to figure out where the rest of the timelines land in relation to this fixed scan out. So let's move up the latency chain. The GPU is what renders the image to the frame buffer. All right, let's say we want the GPU to render a big triangle. That means writing a bunch of data into the frame buffer memory. But where does this rendering actually show up in the timeline? Let's just say that rendering happens here. But remember that the scan-out is continuously reading from the frame buffer and sending data to the display. That means we're simultaneously reading and writing to the same memory. That's a race condition. So what happens is that the first part of the scan-out transmits white pixels because it's before the triangle rendered. And then the GPU swoops in and draws the triangle. And then the scan-out proceeds with triangle pixels. And this leads to some pretty bad artifacts. So we're going to decide on a rule. Don't render into a frame buffer while it's being scanned out. With that rule, is there any time left on the GPU when it's allowed to render? So one solution is to only render when no visible pixels are being transmitted during the H blank and V blank periods. And in fact, really, really old games used to do this when there was only a single dedicated frame buffer available. So unfortunately, this is not practical today because it wastes valuable GPU time. So today, the conventional solution is double buffering. We allocate 2 frame buffers and render to alternate buffers each frame. So while rendering into frame buffer A, frame buffer B gets scanned out, and then we switch and we render to frame buffer B and scan out from frame buffer A. This switching operation is called the flip. So 2 operations have to happen during the flip. First, we toggle which render target we're rendering into from A to B, and we toggle the address of the frame buffer that the scan-out reads from B to A. So there's another problem. It's not sufficient to flip immediately after we're done rendering one frame. So let's say we finished rendering A, we flip, and A starts to scan out while rendering begins for B. Let's say B finishes rendering before the scan-out finishes for A. So what would happen now if we flipped immediately? Then the scan-out would switch in the middle from reading from A to reading from B. And the resulting image on screen would have the top half scanned from A with the bottom half scanned from B. And this artifact is called tearing, and it's most visible when there's large horizontal movement on screen. For example, if we're rotating the camera. So solving this requires a second rule. Only flip when the scan-out is done. In other words, only flip during V blanks. This is called vertical blank synchronization, or VSync. And all of the games that we ship on console have VSync enabled by default. Okay, so I think we're all pretty familiar already with double buffering and VSync, but it always takes me a minute to really understand why they're necessary and what they are. So to review, there's 2 distinct artifacts that we're trying to solve here. First, if you render into a frame buffer while it's being scanned out, we get partial renders in the scanned image. And we fix this by double buffering and never rendering to a buffer that's currently being scanned out. And second, if we flip during the middle of a scan out, we get tearing artifacts between the 2 frame buffers, and this is fixed by only flipping during V blanks, or VSync. Okay, so back to the timeline. With double buffering and VSync, we flip during the V blanks and switch between frame buffer A and frame buffer B each scan out. Let's say we're rendering to frame buffer A. When's this rendering allowed to happen now? So the periods that we're not allowed to render are the big blue rectangles. During the first period, the GPU has to idle, waiting for frame buffer A to become available. But once the scan-out for A is done, rendering is then allowed to start into A. Once the GPU is done rendering, it can't immediately flip A, because that causes tearing. So instead, the GPU queues a flip. It tells the video scan-out hardware that A is ready to be flipped during the next vblank. And this is our first source of slop, between the queue for flip and the actual flip. So if you calculate the slop duration, it's 16.6 milliseconds minus the total GPU workload. But remember how I talked about how we want to be using as much of the available hardware resources as possible? GPU cycles are especially valuable, and we'd be wasting it if GPU workload were consistently low. So if we're doing our jobs well, we'd be drawing more, and we'd be drawing at higher resolutions. So what happens if slop were heavier? What happens to slop in heavier GPU workloads? So when the GPU workload is full, it approaches 16.6 milliseconds, and slop disappears. Remember that we're going to be throttling to squeeze out slop in the latency duration. If there's no slop here, what was the point of looking at this in the first place? In reality, things are a little more complicated. There's actually a huge source of slop here, even with heavy GPU workloads. The reason for that is that most of the draws for our frames are rendered somewhere else, not to a frame buffer. Almost all of our GPU time is spent rendering to off-screen buffers, with the majority of our 3D draws rendered into a third off-screen buffer that I'll call the scene buffer. The scene buffer can be at a lower resolution and can have a different color encoding than the final display. And when we're done with scene rendering, the scene buffer gets upsampled into the frame buffer, usually with some temporal anti-aliasing applied. After the upsample, we render UI elements into the frame buffer at display resolution, and then queue a flip. But the important point here is that most of the GPU frame time is spent rendering the 3D scene, and the frame buffer doesn't get touched until the upsample late in the frame. And this isn't exactly triple buffering, because the scene buffer is never actually scanned out to the display, but the timings work out similarly to triple buffering, so we're going to call this pseudo-triple buffering. So in the original double buffering setup, the GPU needed to wait for a frame buffer at the very beginning of the frame, syncing the GPU timeline with the scan-out timeline. But now with pseudo-triple buffering, the GPU only needs to wait for the frame buffer late in the frame, right before the upsample. And remember with strict double buffering, rendering to frame buffer A was only allowed in the periods between the blue rectangles. And now the GPU workload gets split into two parts: scene rendering, which doesn't use the frame buffer, and frame buffer rendering, which does. The frame buffering rendering section still has to live between the two blue rectangles to avoid mid-scan rendering, but the scene rendering section is allowed to start whenever it wants to. So what happens is that everything gets shifted backwards in time. The GPU starts scene rendering as soon as it's done with the last frame, and frame buffer rendering still has to sync with the scan-out, but it gets shifted backwards too. And that makes the slop calculation a little more complicated. Remember that with strict double buffering, slop was just 16.6 milliseconds minus the total GPU work time. And when we had a full GPU workload, that meant slop basically disappeared. Now with pseudo-triple buffering, slop gets split into two parts. The first slop duration is the frame buffer wait, and that's between the end of scene rendering and the beginning of frame buffer rendering. And the second slop duration is between the queue for flip and the actual flip. If you calculate these two slops, the first one is 16.6 minus the GPU workload, but the second one is 16.6 minus just the frame buffer rendering workload. So what happens when you have a full GPU workload is that we have more scene rendering, more 3D objects, higher scene resolutions, but frame buffer rendering usually stays consistently short. So when the GPU workload is full, the first slop still disappears, but the second slop stays very long. That means that even though the GPU is working at nearly full capacity, it's still possible to have a really huge slop, and that's slop that we can throttle out. In all the games that I've worked on, I found that this slop duration was not being explicitly measured or controlled. So even when the GPU was being properly fed, when you measured the duration, it would either be wandering all over the place, or it would be sitting consistently high at around 16 milliseconds. Okay, but there's another consequence to pseudo-triple buffering. So far, we've been assuming that the GPU workload was always faster than 16.6 milliseconds. But if you're trying to keep the GPU as fed as possible, it's easy to accidentally go over a little and have a slow frame. So let's say rendering for frame B was slower than 16.6 milliseconds. What happens in the strict double buffering case? Well, the frame buffer isn't ready by the upcoming V-blank interval, and we miss the V-blank. No frame buffer is queued for flip, and no flip happens. Instead, the scan-out stays pointed at frame buffer A, and A has to get scanned out a second time. So we have to wait until the next V-blank to finally start scanning out B. And now, because A is being scanned out a second time, we have to wait all the way until the flip to start rendering for A as well. And if rendering for A is also slow, we miss another V-blank, and so on and so on. So what happens is that if our GPU render time is consistently slower than the refresh rate, even by a single microsecond, we miss every other V-blank, and our frame rate gets pegged to 30 Hz instead of 60 Hz. And this is a pretty disastrous consequence, especially if we're trying to keep the GPU workload as full as possible. Now let's look at what happens with pseudo-triple buffering. Assume that we do miss the first V-blank. Frame buffer A still has to get scanned out twice. But now, the scene rendering for A is allowed to start immediately, even though A is still being scanned out. That's because there's no restriction on when scene rendering is allowed to happen. And this is a pretty big difference from the strict double buffering case, where the GPU had to idle all the way to the next V-blank. So even though the GPU workload is still greater than 16.6 milliseconds, A doesn't miss the next V-blank because scene rendering was allowed to start so much earlier. Let's zoom out a bit and look at the behavior over multiple frames, assuming a fixed, slower than 16.6 millisecond GPU workload. So the first frame still misses a V-blank, and A gets scanned out twice. But then the next frame, the next frame, the next frame, they all make their V-blanks. Ultimately, we do miss a V-blank again, but not before we get through 6 frames that didn't miss a V-blank. That means that with pseudo-triple buffering, we don't experience the cliff that pegs us to 30 Hz. Instead, our average frame rate slowly drops from 60 into the 50s. Take a look at the braces at the bottom. These are measuring slop between the queue for flip and the actual flip for each of these frames. Notice that after the first few missed V-blanks, slop is high, but as slow frames go through, slop gradually decreases. So each slow frame eats into the available slop until slop finally drops below 0 and we miss a V-blank. So this illustrates an important point about slop. Slop serves as buffer room for slow frames. All right, so being able to stay in the 50s is probably better than dropping down to 30, but it still creates an unpleasant stuttering effect where you miss a single frame every couple of frames. And we'd much rather stay consistently at 60 all the time, and that's where dynamic resolution comes in. So when the game notices that GPU times are getting slower than a threshold, the engine cranks down scene resolution to stabilize frame times. But no matter what, the game has to experience at least one slow frame before the low resolution can kick in. So there's an intuition that at least one V-blank miss is guaranteed even when you have dynamic resolution. And that would be true with strict double buffering. A single frame over 16.6 milliseconds will guarantee a missed V-blank. So to avoid missing dropped V-blanks with strict double buffering, you'd have to tune the slow frame threshold way lower than 16.6 milliseconds. And you just have to pray that they never spike above 16.6. But let's look again at the timeline for pseudo-triple buffering now that we have now with dynamic resolution. So a few slow frames go by, and we don't miss a V-blank. Slop gets dangerously low, but finally the resolution kicks in. Notice that as fast frames go by, slop actually accumulates back up to safe levels. So the idea here is that slow frames eat into slop, while fast frames build it back up again. Okay, so with the extra slop that comes from pseudo-triple buffering, we're able to tune the slow frame threshold much closer to 16.6 milliseconds, and we have a chance of surviving spikes above 16.6 milliseconds. This property is absolutely vital for dynamic resolution to be a viable technique. Okay, so we've illustrated the fundamental trade-off of latency throttling. On one hand, we want to reduce slop because our goal is to reduce input latency without reducing work. But on the other hand, slop is necessary for surviving a couple slow frames without missing a V-blank. So given this trade-off, how are we supposed to proceed? So here's the plan that I arrived at when looking at the last few Call of Duty games. In the general case, the game should be coded to maximize slop given the engine's buffering setup. That way, in the general case, things will be as safe as possible. And then only at runtime, when the coast is clear, do we introduce a throttle to squeeze out slop and reduce latency. So first, we have to decide on how much the game is allowed to buffer. This is a trade-off between extra memory and increased maximum slop. Take pseudo triple buffering, for example. To me, this seems like a pretty good amount of buffering between the GPU and scanout, because we already have to allocate 2 frame buffers to avoid mid-scan rendering, and we're already allocating a scene buffer to support dynamic resolution. You could always choose to go with true triple buffering or even quadruple buffering, but in practice, there are diminishing returns in terms of safety. All right, so once the extent of buffering was determined, I needed to modify the engine to allow it to achieve the maximum slop. And that means synchronizing buffer access as late as possible in the frame. So what does this mean in practice? Here's a simple example from a recent Call of Duty game. When HDR support was added, the scene buffer to frame buffer split changed a little bit. So first, we perform scene rendering to the scene buffer, and then we upsample the scene buffer to display resolution, but this time to another off-screen buffer. So we render UI at full resolution to this off-screen buffer, and finally, at the very end of the frame, this buffer gets transcoded to the actual frame buffer in its final color space. Note that the first time that we touch a real frame buffer is right before the transcode. And we only use the real frame buffer for a very small portion of the frame time, or about 170 microseconds at 1080p on PS4. Okay, on one platform, the frame buffer was originally acquired at the very beginning of the frame, and we actually shipped this way on an old game. And this totally counteracts the benefits of pseudo-triple buffering, making it behave identically to strict double buffering. And any slow frame guarantees a missed V-blank in this situation, making dynamic resolution less effective. Things were a little better on the other platform. The wait for the frame buffer was inserted after scene rendering, but when HDR support was added, this wait wasn't moved. This setup behaves better than the previous case, but it still causes the frame buffer portion to be longer than necessary. So even though the frame starts earlier than in the strict double buffering case, slop was not maximized, still leaving us with a higher than optimal chance for missing a V-blank. So of course, the correct location to acquire the frame buffer is right before the transcode. This maximizes slop and minimizes the chance of dropping V-blanks. I'd recommend checking your code to make sure that the wait for frame buffer happens as late in the frame as possible. It's really simple to do this, but it's easy to mess up when the structure of the frame changes because it has no effect on performance when VSync is off. So with DX12, the wait happens when performing a transition barrier on the frame buffer resource from present state to the render target state. And there are equivalent functions on other APIs. I'd also recommend timing these waits. You can stick GPU timestamps around these calls and incorporate them into your GPU timing system. So what we have to do is subtract the timing of this wait from the total GPU time to get accurate frame timings when we have VSync enabled. Okay, so we've discussed the GPU to scanout relationship and identified the potential slop here. We've concluded that slop can accumulate here even when running with full workloads, but that some slop is necessary to avoid missed V-blanks. Okay, let's move up to the next link in the chain, the CPU to GPU relationship. So a large portion of the CPU's workload is spent telling the GPU what to do. That means recording state changes, draws and dispatches into command buffers for the GPU to consume, as well as generating associated rendering data like dynamic vertex and index buffers. The buffers written by the CPU and read by the GPU are either double buffered or allocated from a ring. And after the CPU has built up a command buffer, it tells the GPU to start working on it through a kick. The kick event is analogous to the frame buffer flip between the GPU and scanout. And just like with the GPU to scanout, slop can accumulate here between the CPU's kick and the GPU actually starting the frame. Okay, but something that's different from the GPU to scanout system is that the CPU records commands in approximately the same order that the GPU consumes them. So for example, a frame on the CPU might consist of recording commands for a prepass, then commands for shadows, then commands for opaques, and so on. And after the kick, the GPU then draws in that order too. So we take advantage of this by splitting the buffers that are shared between the CPU and GPU at a finer granularity than one frame. So instead of the CPU generating all the data for an entire frame up front and kicking the whole thing once, the CPU instead makes multiple smaller kicks per frame. So the CPU kicks immediately after recording the data for the first half of the prepass, and the GPU starts working on the prepass, while the CPU simultaneously records the data for the second half of the prepass. This allows for significant overlap between the CPU and GPU frames. To correctly account for how latency works in the overlap situation, we have to modify our definitions of slop and work. So in the non-overlapping case, slop was the segment from the end of the CPU frame to the beginning of the GPU frame. And remember why slop and work were defined this way. So when throttling, work is the part of the latency duration that moves forward in time, but doesn't shrink, while slop is the part of the latency duration that does shrink. So now with the overlapping case, the GPU is allowed to start working immediately after the CPU makes its first kick. That means we have to define slop as the range between the CPU's first kick and the GPU starting the frame. And work would be everything else, the duration between the beginning of the CPU frame and its first kick, plus the entirety of the GPU frame time. Notice that by just allowing overlap, we've significantly reduced our definition of work. What I'm not saying is that the CPU and GPU are forced to overlap. There could still be a delay between the end of the CPU frame and the beginning of the GPU frame. What happens is just that our measurement for slop would be much higher because the GPU could have started much earlier. So by implementing overlap, all we've done is allow the throttle to squeeze further than it could have in the non-overlapping case. Let's talk about performance. So remember that GPU cycles are typically the most precious resource. In Call of Duty games, we're more likely GPU-bound rather than CPU-bound. So in the ideal case, the CPU would be consistently faster at recording commands than the GPU is at consuming it. That way, the GPU would never be starved and never be idle. But if one of the CPU segments gets kicked too late, the GPU can go idle. This is called a GPU bubble. When the GPU and CPU are significantly overlapped and the GPU is only slightly behind the CPU, the risk of bubbling is much higher, especially early in the frame when individual draw calls retire faster. Bubbling is inefficient because it means idle GPU cycles, but it can also bias the GPU frame time measurements that we use for dynamic resolution, causing unnecessary resolution drops. But if there was some slop between the GPU and CPU, that slop can serve as buffer room to minimize the effect of CPU spikes, yielding a smaller bubble or avoiding bubbles altogether. So this leads us back to the fundamental trade-off. Low slop means more overlap, so lower latency, but it also means bigger bubbles on the GPU if the CPU can't keep up. Higher slop means less overlap and higher latency, but CPU spikes can be more easily absorbed, avoiding GPU bubbles. So a ton of effort over multiple generations has gone into making sure command buffer recording works as fast as possible. I'll quickly name just a couple techniques. So the most important is running wide over all available cores instead of recording on a single thread. We do this by recording the individually kicked segments as separate jobs in our job system. And to get these jobs to run as fast as possible, we have to take special care in tuning the granularity that the frame gets split up, and also reducing contention between jobs over shared resources. And other techniques to optimize command buffer generation include reducing draw call counts through instancing and a variety of CPU culling techniques, and reducing the overhead of draw calls by minimizing state changes and using techniques like bindless. Okay, so now we have super fast command buffer generation that runs wide over multiple cores, and one thread picks up all the finished command buffers and then kicks them to the GPU. And in the ideal case, the GPU is running slower than the CPU, so it stays solid and fed for the entire frame. Fortunately, we don't always get the ideal case. Maybe one of the draw jobs started late, or maybe it got kicked off of a core by a system thread, or maybe it just had too much work to do. The submission thread has to wait for the job to finish before it can kick the command buffer, and if that wait is too long, the GPU goes idle and we get a bubble. But there's this cool thing we do to try to avoid bubbles in this situation. The submission thread's wait for the draw job has a timeout. If the job doesn't finish in time, we set an abort signal telling the job to stop. This job periodically checks for the signal, and if it detects an abort, it stops iterating and it ties off its command buffer. Then the submission thread takes over the job and performs all of the work that the job would have done. But this time, instead of kicking only at the end of the job, it kicks much more frequently. So by kicking more frequently, the CPU gets spoon-fed bits of work a little sooner than it would have had we waited for the job to finish. So this comes at the cost of extra CPU and CPU overhead to frequent kicking, but it reduces the impact of bubbles or avoids them altogether. Remember that the draw job has to periodically check if an abort has been signaled. In really, really bad situations, this check doesn't happen soon enough after the abort. For example, if a system thread kicks the job off of core for a long period of time. So even though the submission thread signaled the abort, it could still be forced to stall for a long period waiting for the job to finally give it up. We try to get around this by having a second timeout on the abort itself. If the draw job doesn't abort soon enough, the submission thread starts the whole job over again from the beginning, again with frequent kicking. This case is more serious than the clean handoff scenario, but it still avoids or lessens the impact of potential bubbles. Okay, so we've gone over the CPU to GPU relationship. They're allowed to overlap, which can significantly reduce latency once we have the throttle. And we've tried very hard to speed up the CPU workload to avoid GPU bubbles, but there's still a chance for bubbles if there's not enough slop between the two. Okay, let's go up to the final link in the latency chain. I oversimplified by treating the CPU frame as a single monolithic block of work. There can still be sources of slop here, between the threads on the CPU. To look for these sources, I'll introduce the client frame and render frame split. So here's a very high-level overview of one frame of CPU work. There's a ton of other systems involved, but this is just a summary. So first, we get an authoritative game state from the server to update the client game state. Then we sample for input and factor that input into client-side game simulation. And finally, we do all the work necessary for rendering the result of the game simulation to screen. Let's zoom in on the rendering part. So rendering is split into a bunch of little jobs. This includes traversing the scene graph, culling, picking LODs for models, and so on. The final output of all of these little jobs is a set of visible surface lists. Jobs are then assigned to iterating each of these individual lists, and these are the jobs that generate command buffer and associated rendering data. And finally, one job collects all the completed commands and kicks them to the GPU. This job also records commands not included in the surface lists. For example, decompressing surfaces, post effects, and 2D drawing. So conceptually, all this work can be categorized into three groups: scene preparation, drawing, and GPU submission. So back to the high-level view of the frame. All of this work is heavily multi-threaded and runs as wide as possible, but on average, scene preparation and drawing are the parts that benefit the most from running wide. So the beginning and end of the frame achieve lower utilization over available cores, leaving more idle CPU cycles on the table. So to keep the CPU cores more consistently saturated, we split out the drawing and submission work. Then after this frame's scene preparation, we immediately start the next frame. That way, the beginning of the next frame overlaps with drawing and submission for this frame, and this yields a pretty huge speedup. So conceptually, we call everything up through scene preparation the client frame, and a dedicated client thread coordinates all of the associated work. A second render thread performs all of the command buffer submission, post effects, and 2D drawing. And in between these two timelines are all the drawing jobs that generate command buffer. The client launches these jobs, and the render thread waits for them and kicks their result. Just like with the other producer-consumer pairs, slop can accumulate here between the client and render frames. But let me focus a bit on how we do synchronization and how that used to work between the two timelines and how it affected slop. So first, the client has to synchronize with the GPU because it writes into shared buffers used for scene rendering. These resources are double buffered, so before the client can start its frame, it has to wait for the GPU scene from 2 frames ago to finish. And the client and render threads also have to share data. Originally, the render thread wasn't allowed to start a frame until the beginning of the next client frame. So if you zoom out, on the bottom is the GPU timeline. The beginning of the client frame synchronizes with the end of the GPU scene rendering from 2 frames ago. So it lands here. The beginning of the render frame then synchronizes with the beginning of the next client frame, so it lands here. And this creates some slop between the end of the client frame and the beginning of the render frame. So my question is, why does this slop actually exist if we're not bound on the render thread? I claim that there's actually no correctness reason why the render frame couldn't have started here instead, right at the end of the client frame. But making this change has no effect on total latency. The total slop across the frame stays totally the same. It just moves from the left of the render frame to the right of the render frame. This is where I introduce a second goal after maximizing slop. For safety, I think it's a good idea to move slop forward in time as much as possible. And let me go over why this is good. Remember that slop is what protects us against spikes, but not all slop in a frame protects us equally against all possible spikes. So for example, if the client frame spikes, all sources of slop later in the frame are available to absorb the spike and avoid a dropped frame. But if only the GPU spikes, only the slop after the GPU can absorb the spike. So because slop later in the frame can absorb any work before it, it's always better to keep slop as late in the frame as possible. And the way to accomplish this is to make sure that synchronization lets work start as soon as it's legal to do so. So for example, letting the render frame start at the end of the client frame instead of at the beginning of the next client frame. Okay, so we've changed the synchronization to allow the render frame to start immediately after the client frame finishes. Now remember why the render and client frames weren't allowed to run concurrently in the first place. It was because the client writes into buffers that are read by the render thread. In fact, we can start the render frame even earlier, allowing it to start before the end of the client frame. This overlap is implemented in one branch of our engine, and it doesn't yield as dramatic latency savings as the CPU to GPU overlap, but it still does claw back a few milliseconds. We achieve this overlap by splitting the shared data between the client and render threads and minimizing dependencies between those splits. So the extent of the overlap that's possible depends on how far back in the client frame we can enforce the split. So for example, if segment A is to be kicked before segment B, the work that A depends on needs to be executed by the client before the work that B depends on. And this allows A's draw job to be started as early as possible in relation to B's draw job, and thereby allows the render thread to kick A to the GPU before work for B is even done. So that means we have to alter the definition of slop between the client and render frames. Now it's the delay between waking the render thread and the render thread actually starting this frame. Okay, one last thing about synchronization. Remember that the client can't start until the GPU finishes the scene from 2 frames ago. This protects access to double buffered data shared between the CPU and GPU. However, those buffers are only ever written to by the CPU during rendering related operations. That means scene preparation, drawing, and submission. All of the client simulation work in the first half of the frame doesn't touch GPU visible buffers. That means we could move that wait later in the frame, right before writing into any of the shared buffers. And with this change, the client frame gets split up into 2 parts. One segment before syncing with the GPU, and one segment after syncing with the GPU. So the GPU wait is now after the input sample, so this introduces a new slop into the latency path. And this is another example of maximizing slop in the general case for safety. Okay, so now we've looked at all the major timelines in the engine and identified all the segments of work and slop in the latency path. So 5 segments of work were identified. 2 segments in the client frame, first between sampling the controller until syncing with the GPU, and the segment after syncing with the GPU and waking the render frame. Then in the render frame, the time between waking up and kicking the first command buffer to the GPU. And in the GPU frame, there's the scene rendering segment and the frame buffer rendering segment. And everything else is slop. The client waiting for the GPU scene, the time between the client signaling the render thread to wake and the render frame actually waking up, then the time between the render thread kicking the first command buffer and the GPU starting the frame, and the GPU waiting to acquire the frame buffer from the scanout. And finally, between the GPU queuing a flip and the actual flip to the scanout. So now we're going to incorporate all this information into designing our throttle. So we're introducing the throttle right before the input sample, so that the sample and subsequent work are delayed and shift to the right. Notice that as we throttle, slop gets squeezed out starting from the left, but the total work stays the same. So now we've throttled enough that there's no longer any slop between the client, render, and GPU. The only slop is between the GPU and the scanout. And now this is the maximum throttle we can introduce, leaving 0 slop in the frame. If we delay just a bit more, we miss a v-blank, and we miss a frame. OK, so the question is, how long are we supposed to throttle? So we know that we're in the middle of the client frame, right before the input sample. We know that the end of the latency duration is during a future v-blank, when we want this frame to get flipped. And so what makes up all the time in between now and the v-blank? First, there's our throttle that we're solving for, and there's work and slop for the rest of the frame. So solving for the throttle, we get the duration between now and the flip minus the total work and slop. But remember that we're near the beginning of the frame. Before the frame runs, we have no idea how much work and slop there's going to be. So instead, we have to estimate how much work there's going to be this frame, relying on previous frame data. And we have to decide beforehand on a target slop value that we want to achieve for this frame. So the problem then becomes, given target amount of slop, how long should we throttle? Let's start by looking at how to find the time of the intended flip. So we have to calculate the absolute time of the v-blank when we're aiming to flip. And because v-blanks come every 16.6 milliseconds, you just have to timestamp previous v-blanks and extrapolate. So typically, we use a dedicated high-priority thread to listen for GPU interrupt events, like flips and v-blanks. And sometimes the API exposes the display driver's internal timestamp for these events, or you can just timestamp them yourself on the CPU. And I haven't noticed a huge discrepancy between these two methods for timing. On Xbox, you can get the dedicated thread. You can also use the dedicated thread, but Microsoft also provides us with a convenient helper function for getting a bunch of frame timings. So you pass the engine's internal frame index to present as the cookie parameter, and then you call dxgi get frame statistics, and that returns an array of structs that includes v-blank, qflip, flip, including v-blank, flip, and qflip timings. And all those timestamps are in both CPU ticks and GPU ticks, which is really convenient. Also, each of these structs includes a cookie field that you can use to line up internal engine frames with those statistic structs. OK, so now we have to forecast how much work there's going to be this frame. And that means timestamping every segment of work every frame. And before the throttle, we collect the most recent measurements and sum them up to get a total work estimate from the previous frame. Because the throttle is in the client timeline, the client work measurements don't need to be double buffered. Instead, we just read back the timings from the last frame because they're guaranteed to be complete. But because the client frame runs concurrently with the render and GPU frames, there's a chance that the work duration will be in flight when timestamps are collected, creating a begin timestamp that's after the end timestamp. So instead, we just double buffer these timestamps on non-client timelines. And at least one of each pair of timestamps should be valid. So we compare the begin and end timestamps of both pairs to figure out which one is valid and which one is most recent. And then we use the previous frame's work measurements to make a forecast for how much total work there's going to be this frame. Unfortunately, work is unavoidably noisy. Content changes between frames, and the performance of some systems can be spiky or exhibit cyclic behavior. So to reduce variance of when input gets sampled and to lessen the impact of spikes, we exponentially smooth previous work measurements to get a forecast for this frame. We also tested double exponential smoothing, where we estimate and smooth velocity as well. So the rationale behind this was that work times also tend to follow multi-frame trends. For example, when turning the camera from a low complexity scene to a high complexity scene, work will increase each frame. Unfortunately, we found that this had to be significantly damped to avoid wandering and v-blank misses, and was ultimately abandoned. OK, finally, we have to decide on a target value for the total slop accumulation during this frame. And deciding on an ideal slop target depends on two questions. First, how much do we value reduced latency versus the risk of missed v-blanks? And second, how spiky is the amount of work this frame? So the first question is a value judgment and depends on your level of risk aversion. The second question, however, can be quantified by keeping a history of work measurements from previous frames and then calculating variance. We settled on a tunable function for target slop based on this variance estimate. We start with a baseline target for slop of 6 milliseconds, and then we ramp up this target as variance increases past the threshold. If work variance grows past a larger threshold, or slop goes under a safety threshold, we turn throttling off completely to give the biggest chance for the engine to recover without missing a V-blank. Okay, so now we've directly tied the problem of input latency with the problem of frame variance. Reducing frame variance can be tricky and requires a team effort. And I don't have any clear-cut directives for how to reduce frame variance in general, but here's a couple practices that help me. So first, adding in-engine variance measurement for high-level workloads was helpful in identifying where the major sources were coming from. Many sources of spikiness were due to poor job scheduling, where critical jobs would be picked up early in some frames and too late in other frames, or would be picked up by a core that has frequent system thread intrusion. These kinds of issues were usually fixed by rescheduling when the jobs were queued or tweaking which cores the job could work on. A tool that was invaluable for identifying spikiness problems was a lightweight marker-based profiler. An example of one that we use internally is called JQProf, and that's shown here. The workflow is super simple and non-invasive. Timestamps are just dumped to a file, and the tool just renders simple boxes for markers. While more advanced commercial or IHV profilers are crucial for deep dives into particular systems, the capture and analyze loop for lightweight tools is so much faster. Also, the code for this tool is dead simple, so I usually just keep it checked out in Perforce and just add one-off features as necessary. So one of these one-off features that was useful is to quickly scroll between frames while keeping the beginning or end of an arbitrary per-frame marker fixed on your screen. So this lets you quickly eyeball shape differences between frames. And moreover, by keeping a specific marker from each frame stationary on screen, you get an idea for which timeline is being spiky or landing at spiky times in relation to another timeline. Then you can dive further into seeing why that job for that spiky timeline was that's starting early or starting late. And then you can go up the chain of dependencies to figure out why that's happening. So while it's good to always get numbers, especially for validation, I think visual inspection can be more powerful for these kinds of search and destroy tasks. Okay, so we've discussed each of the terms needed to calculate the throttle. We figure out when this frame is supposed to be flipped by timing previous flips. We make a forecast for the total work this frame by smoothing measurements from previous frames. And we decide on how much slop to allow this frame with a heuristic based on work variance. And using these terms, we then calculate how long the client frame needs to sleep before sampling for input. Okay, but let me step back for a second and ask, why do we have to go through the process of identifying every source of work and slop in the engine? So the key benefit is that it makes predicting the slop for a given throttle much simpler. So given a static frame, increasing the throttle makes work for throttle a flat line. On the other hand, slop becomes a straight negative line for the same when you increase throttle. So this makes calculating an appropriate throttle very easy if you're given a target slop amount. The measured slop then converges to the target slop in one frame. But couldn't we have just treated the whole engine as a big black box? When I was first looking at latency, this is how I thought about the problem. I called everything inside the big black box work, and the only slop was the duration from the Q flip to the flip. This ignores all of the extra sources of slop inside the engine, but it makes work measurement so much easier, and I expected the throttle to still work in this case. The problem is that throttling is no longer predictable. Some initial throttling squeezes work, but doesn't affect slop. So as you increase the throttle, work decreases for a little while, but then flattens out, and slop stays flat for a little while and then decreases. And so you lose the linear relationship between throttling and slop that makes it so simple to calculate the proper throttle for a given slop target. And that's because you don't know where this corner lives up front. Instead, you have to search the throttle space to find the correct throttle amount. And searching instead of solving is doable on static workloads, but convergence to the target slop takes at least 2 frames. And I found that slop would wander around too far from the target, causing either huge amounts of latency or too many missed V-blanks. So instead, I had to unpack the big black box and figure out exactly where all the sources of work and slop were. Okay, one last implementation detail. There's not that many systems in our games that dynamically alter the behavior based on performance measurements. The only other example I can think of is dynamic resolution. And feedback systems like this need to be especially careful about being robust to weird inputs and edge cases. I'll illustrate an example of a bug in the throttle that wasn't discovered until quite late. So the throttle has to subtract a work forecast and a target slot value from the intended flip time. And the work forecast and target slot values are relative durations in the range of multiple milliseconds. And I assumed that the extrapolated flip timing was absolute, probably huge if it's measuring since an epoch. And absolute minus relative should be safe. But I assumed wrong. On one platform, the flip timings were actually recorded since the beginning of the game of the launch of the game, not since an epoch. And usually that didn't matter. Flip timings would start in the range of seconds and then go up into the minutes, while work and slot timings would stay in the milliseconds, except when process lifetime management kicks in. So take this scenario. Let's say you play the game for 30 minutes, and then you suspend the game and go to sleep. So what happens if you start the game again 8 hours later? Well, the first frame's intended flip time would be extrapolated from 8 hours ago. So it would come out to 30 minutes plus a couple V blanks. And what about the work forecast? If the game was suspended in the middle of a work duration, the work measurement would span the entire suspension period, and you'd get a measurement around 8 hours. And even with smoothing, you could end up with a huge work forecast that's longer than 30 minutes. And if you're using unsigned ints, like I was, the wait time wraps around and the game hangs. But this bug only shows up after suspending the game for longer than the game has been running, which is not a test case that I ever test for. So the moral of this story is that you have to be extra careful in validating all of your measurements at runtime, because in the wild, the throttle is always active and continuously feeding back on itself in the shipped game. Okay, I'll touch on specific improvements that were made during the development of a recent Call of Duty game. Before implementing the latency throttle, the engine's data flow had to be audited to identify which segments to measure so that work and slot could behave correctly when throttled. And this process uncovered multiple performance and correctness issues that impacted frame times in certain CPU-bound scenarios, and solved some bugs and crashes due to improper synchronization. On one platform, the throttle clawed back around 5 milliseconds of latency on average multiplayer workloads. And the reason why this is relatively low is because the wait for frame buffer was very early in the frame. And that meant that the slot between the GPU and scanout was already quite low. And moving this wait later in the frame actually increased latency in the general case, but allowed for dramatically fewer V-blank misses in heavy game sections. On average frames, though, the throttle then brought latency back down to a little lower than previous levels. And on another platform, the wait for frame buffer was already late in the frame, so no major loosening was required. Instead, the slot between the GPU and scanout was consistently high during those typical workloads, and that meant that the throttle could claw back around 22 milliseconds of latency on average multiplayer scenes. Okay, so I'll finish with a couple recommendations for looking at latency and performance in general. First, I would recommend keeping vsync on by default during profiling. We have this organizational intuition that vsync should be kept off during profiling because it somehow skews the numbers. But we ship with vsync on, so I think it makes more sense to figure out why vsync is skewing your numbers and to keep it on all the time. Second, I would recommend implementing in-engine latency measurements and an on-screen timer. So we have dedicated GPU timers and CPU timers, and those are super useful for diving deep into specific systems. But I think to get a global view of what the frame is like, it's good to have a timeline that unifies both the GPU, CPU, and scanout timelines. I'd also recommend mapping the data path from the input sample to the scanout in your engine to make sure that the synchronization is correct and everything is as tight as possible. Finally, I would also recommend thinking about frame time variance as a first-class performance metric and periodically looking for ways to reduce it, because it's directly responsible for how far you can safely tighten your game's input latency. I'd like to thank Wade Brainerd and Michael Vance at Activision Maine for their guidance and mentorship. I'd also like to thank Infinity Ward, Sledgehammer Games, and Treyarch. Thank you. I think we have time for one question.
Do you have a deterministic game engine with regards to physics and like input samples versus update frames?
No. But we run at 60 all the time, so it's like okay.
So would you say on average you sample input once per rendered frame?
Yes. We only sample once.
Do you always only sample input once per rendered frame?
Yes.
Okay.
Okay, I just wonder, do you ever consider using, for example, FreeSync?
FreeSync?
Yeah.
Oh, so I mean, so on console, support for variable refresh rate is coming soon. We currently don't support FreeSync. It's sort of an interesting question what you should do in those kind of situations, because basically what happens with G-Sync or FreeSync is that the scanout is no longer the
You can be
binding
much
timeline.
safer to be.
Yeah, you don't miss V blanks, right?
Yeah,
But there can
right.
still be slop between the GPU and CPU.
Sure.
So you can still throttle a little bit, but latency is already much better.
But you can be much aggressive.
Much more aggressive. I know, but we still want to stay at 60, I think, or maybe
Okay.
higher.
Okay.
Yeah, you can be more aggressive, though, definitely.
Okay.
Yeah.
And another question?
Yeah.
For example, on the Windows platform,
Yeah.
even the main thread can be preempted.
Sorry? Oh, even the main thread can be preempted?
Yeah, how do you deal with this?
I'm not sure, sorry.
Okay.
I think Windows is hard.
Okay, thank you. Great talk. Very detailed. Thank you.
I was wondering, is variance in input latency a consideration when you're doing this throttling?
Yeah, so that's actually an important question that I don't know the answer to. I think that the research shows that it does matter for satisfaction. But I mean, input is already sampled at quite terrible rates. So I mean, there's already quite a bit of variance, even when you have a fixed time during your game that you sample for it. But you're right that this could be adding it. But the fact that we smooth it kind of makes the transitions a little bit smoother. But you're right that the variance is still important in the input sampling time.
Thank you.
Sorry, do you do congestion control on your network snapshot demo?
Sorry, I know nothing about networking. I'm really sorry.
Fair enough. Okay.
Probably. All right, thank you.